In the name of God, the compassionate, the merciful, engineering plasticity, Chapter 5, Elastic Plastic Analysis of Bending, Part 6. In this part, we are going to talk about a special method for solving difficult problems. The beam shown in here is a built-in beam, okay, fixed at two ends, and there is a load W at the middle of the beam. If we increase this load so that we get complete plastic deformation, so here we have complete plastic bending moment, obviously here, and there also we have complete plastic bending moment. We call it MP. Now, if we want to find out what MP is from our usual relationships and calculations and computations we have learned in the strengths of material, this is an indeterminate problem. Okay, we cannot solve it from our usual ways. So we are going to solve it in a different way. We are going to introduce the concept of collapse load and also the concept of principle of virtual work. Okay. Now, virtual work, what does it mean, virtual work? Virtual work is a concept that we use for solving static problems like this by assuming that the members move, because work is done when a member such as AB or AC or BC moves. If a member does not move, we say it doesn't do any work, no energy is done, although there is bending moments in here, but as soon as it moves, the work is done. Obviously this is a built-in beam and it cannot move, but what we assume is that we assume some plastic hinges. What does plastic hinge means? These points shown in here, we assume that when the beam becomes completely plastic, there forms points or zones in here. There are some zones in here like A, C, and B, which are completely plastic. Okay, because here we have maximum plastic bending moment, here we have maximum plastic bending moment, and there as well. So, for instance, this point here has less moment applied at it than this point. So if we increase W, the first point that reaches the plastic moment is this point, and that point, and that point. No other points reach their maximum. So we could assume that these 3 points become completely plastic, and when they become completely plastic, then we call them plastic hinges. Hinge is something that a door or a member revolves around it. So in here we assume that this member AC and CB act as a mechanism like that. AC moves down to here and BC moves down to here. Obviously this is not true. That's why we call it virtual, not real. It doesn't happen in real life. We just assume that it happens. That's why we call it virtual. And if we assume that W moves 1 meter per second with a unit speed, 1 meter per second, then the work done is W times 1 meter per second. Okay, so that's the rate of work done, that's the power, but the work is W times this distance. Okay, now, so we call this virtual work because this is not real. This is what we have assumed. It happens virtually. Okay, so in this beam we have taken these 3 points as being plastic hinges, then we have taken this something like a mechanism, and we say that that's a hinge, and that's a hinge, and that's a hinge. So this move. Obviously, if C wants to move to this point, it should elongate, but we don't consider that. Okay, this is virtual work, and these are not real life happening, so we do not take that into account. Okay, let's see what we can do with this. Now, the rate of rotation of each link, these are the link AC and CB. It says the rate of rotation. If the lengths of each link AC and CB are equal to L, and C is moving 1 meter per second, so that link moves 1 over L. Okay, that's the rate of rotation. It revolves around A, which is a hinge, and this member also revolves around B, which is a hinge, so that moves 1 over L, and that moves 1 over L. So the rate of dissipation of energy at A and B, okay, because we have a force here W, which has caused maximum plastic moment at A and maximum plastic moment at B. Okay, so fully plastic. This is fully plastic. This is fully plastic. So the rate of dissipation of energy, okay, is, or work, doesn't matter, dissipation of work or energy, that's the power again, mp over L, because 1 over L is the speed or the rate of rotation, okay, and mp is the plastic moment. Okay, so if we multiply mp times 1 over L, we get the rate of dissipation of work. This is the internal work, that's the virtual work, that's the internal work. So we equate the internal work equal to external work, which is the virtual work. Now, also for this point C, we have movement there and we have movement there, so it's 2 mp divided by L, because here also we have mp, but C is moving with these 2 links, so it has twice the speed, so we have 2 mp over L. In other words, it's 2 over L times mp, and if we add up this together, so we got 2 mp over L for this point, we have mp over L for this point, and we have mp over L for that point. So we get W times 1, which is the virtual work, which is what we assumed at the beginning. In other words, we put the internal work equal to external work, and W times 1, which is the unit speed, is equal to 4 mp over L, and from here we get Wp equal to 4 mp over L. See, that's how we use the virtual work principle and plastic hinges to solve this kind of problems, and we couldn't solve this in any other way, okay, analytically. We could not solve such problem analytically. You could use the finite element analysis or simulation to do it, but you cannot solve it in any other way. So this is a very, very simple way to solve such a problem. And if you remember, elastic load required to do some elastic deformation for E over L. Now in here, if we increase this ME to MY, we get 4 MY over L. That's the limit we can go for the beam before being yielded. Okay, that's the yield point. But in here we have gone that far, 4 MP over L. That is much greater than this. So this kind of computation could be used for design purposes as well. I will talk about this. It means that you can use the plastic capacity of the beam in order for the beam to carry out more load. Okay, because if you use the elastic capacity, you can go only up to my. But if you use the plastic capacity, you can go much further, maybe twice the load or more, and still the beam stands and it does not fail. Okay, and this value of MP is the fully plastic moment, but we could use a moment less than this but much higher than this in order to use the capacity, plastic capacity of the beam to carry out more load. I could put it in another way. If you put here my over L, 4my over L, and put here 4m over L, so that m is much higher than my, then you get a much higher WP than WE. Okay, and the beam does not fail. That's the most important thing. It does not fail. So you can use it in design problems where we have the situation that we want to use smaller beams, lighter beams, that kind of things. We take advantage of the plastic capacity of the structure. Now let's go and examine another problem in structural parts or beam. Now this beam also is a built-in beam, but it's a bit different. In the previous example we had just a point load, but here we have distributed load. Okay, and obviously we assume a rigid plastic material in this kind of solutions. Now here we have this distributed load, that's W. In here, in this example, this W is not the load per unit length, it's the total length. So that's why we have shown it with capital W. Otherwise we would show it with a small w. Okay, so that's the beam. 2L is the length. So we know that at the built-in ends, at these two ends, A and B, we would have maximum plastic moment, or the complete plastic deformation. A and B, these are hinges, we know that. But because it's distributed load and it's not symmetrical, we cannot simply find out where the other hinge would be. So we take it at some point in here, because we are sure that it will be some point in here. It won't be here, okay, because the load is distributed here. So it should be somewhere here, like that. That's why we call that A, D, that's the middle point, C, and that's B. Okay, that's why we have used this parameter xi. That's xi times L. So that's just a parameter, just a factor, times L, which makes it less than 1. That's xi is less than 1, so times L becomes less than L. So that's xi L, and that's 2 minus xi L, because that's 2L minus xi L is 2 minus xi times L. Also we take this angle alpha, and we take this angle theta. Okay, so if these 3 points are plastic hinges, then our moments will be something like that. We are not sure how this is, but we know that this point is maximum bending moment or completely plastic. Here is complete plastic, and here as well, where we have these three hinges. Now let's use some geometry here. xi L is this distance. Okay, so if you go there in this triangle here, that distance is xi L times theta is that distance. Okay, that distance. Similarly, 2 minus xi L is that distance again in that triangle here, and times alpha is equal to that distance. So this distance is common to both triangles, and therefore we could equate these two together, and from here we get alpha in terms of theta. Obviously xi is not known yet. Now, using the virtual work principle, in the previous example I used the power equations. Here I use work equation. Okay, in the previous example we used the rate of work, which is the power, but here we use the work. Now, work obviously is force times distance. Now, for this distributed load, as I said, W is the total load of this distribution. So if we want force per unit length, small w is W times L. So that's the small w. Okay? And times the area gives us the work. What area? ADEC. ADEC, corresponding to this distributed load. We know this from the strength of material, of course, because this is a distributed load and it's changing as we go from this end towards C. So we get different values in here, and therefore that's how we show it. Okay, that's the work done. And the internal work, of course, that's the virtual work. If we suppose that it is moving, here we are supposing that this AD, somewhere in here, AD, and BD, B is here. Okay, are two members, two links that under this load move that much. Okay, so that's why we have written this as virtual work, because it's not real. Now, what causes this virtual work is the internal. This virtual work, in fact, is equal to the internal work. What is the internal work? Is the moments we have taken here. MO is the plastic moment, complete plastic moments here and there. So here we have MO is moving this link, so MO times theta. Theta is the angle. Okay, here we haven't taken the angular speed because we are not using the power or rate of work. We are just using work. So that's Newton meter. Okay, and MO also at this D moves that much, so that link moves theta, and this link moves alpha. So alpha plus theta times M0 at the middle, not middle but here at D. And at this end we have MO and moving alpha, so MO times alpha. That's, we equate the virtual work to internal work, and I'm going to substitute for this. So let's have a look. This xi L is this distance, okay, and xi L theta, because we are working in here, you see xi L is this distance, and xi L times theta is this distance. Okay, so that distance times that distance is this area. So I get the area of this triangle plus this part here. So area of the triangle is half XIL from here to there, that triangle. Okay, XIL theta is that, so that length times that length. Therefore, this height of the triangle times the base of the triangle divided by 2 is the area of this triangle. And then for this part, okay, this part, we get again XIL theta, which is this length. XIL theta is this length. Alpha L is this length. Alpha L. L is that part. Okay, L is that part. BE times alpha is EC. So I have that length. And that length, add them together, divided by 2, and times 2XIL. 2XIL is that much. Okay, 2 minus XIL, sorry. 2 minus XIL is that much, minus L. I get this part. So this part, this length times the these two, sum of these two divided by 2 gives me the area of this bit here. The area of this bit here plus the area of this triangle is this, is area of ADEC. So I substitute area ADEC in here, and I get, obviously I should simplify. I simplify this, and I get that and substitute it here. If I substitute it there and then rearrange this, I can get M in terms of MO and XI. Okay, theta and alpha and everything is using this relationship. Alpha in terms of theta, substitute here, then alpha is everything will be in terms of alpha, and we can omit alpha, and we get this relationship. Okay, if you use that, you get this relationship. Now this relationship, we have this xi, which is not known, is our unknown. So how do we find that? If we do a differentiation and put it equal to 0, because that's the maximum point. So if we put it to 0, partial differentiation of w with respect to xi, put it equal to 0, then we have this relationship here. So put it equal to 0, we get xi equal to 3/4, and w becomes 64/9 mo over l. So xi l is 3/4 of l in here. So since l is known, point D is known, and substituting back in here, we get w equal to 64/9 mo divided by l. So in this kind of problems also, you can see that we can solve it very easily using the hinge, plastic hinge, and collapse load. And why we call it collapse load? Because if this MO reaches that, in fact this is for the complete plastic deformation here, completely plastic. MO is complete plastic moment. Okay, this plastic moment is complete. So if MO reaches that value, this W is the collapse load, which means that the beam collapses. Also in the previous one as well, in here, this is the collapse load. That's why I said that we can use the plastic capacity if we use a value less than MP. If we use a value for moment less than MP, then we can use the plastic capacity, which is much bigger than this, and it doesn't yield, it doesn't fail. or collapse. Okay, so that's a collapse load, we call it, because it causes our structure to collapse. So that W is the collapse load. As you can see, these kinds of structures and many more complicated structures, we can use this idea of virtual work and plastic hinges and solve it. The only thing here is that we should know where the plastic hinges are. Okay, we have to guess this. Obviously, in this kind of problem, it is easy to guess. For instance, here and here, we definitely know plastic hinges form there. But in here, we don't know, so we put some parameter and then find the parameter from the optimization. Okay, so minimizing or maximizing, putting it equal to 0, we could find out the position of this collapse load as well. But in other more complicated problems, you don't know where the collapse load is and you have to guess and then solve the problem, and maybe you have to have many guesses and solve the problem for all the options and then see which one is correct. I will get to that in a few slides. Right. Now let us see this bending moment distribution, how really it is, because we just knew that MO is here and another one is here and another was here, but the distribution we didn't know how it was, and we just drew these lines. We didn't know how the shape of these lines should be, but we can get the shape of these lines here very easily. We know that this W is the total load in here. Okay, so should act somewhere in here as a point load, should act somewhere in the middle. So because L is equal to L, so that becomes 3/4 of L from here and 1/4 of L from here. RA is 3/4 of W and RB is 1/4 of W. Okay, because this W is acting at the middle of AC, so it's 1/4 from it there and 3/4 from there. The reaction here bears more load and the reaction here bears less load. So if we consider the section from A to C, which is for half of the beam, is x equal to or greater than 0, x is moving from here to L, so x is moving from here to L. If you consider this section, for instance, M is equal to minus MO plus 3/4 of W x. Okay, 3/4 of W x, because we have 3/4 of W is the reaction here, and times x gives us the moment. This reaction is in the direction opposite to this, the moment. So that if you take that minus, that's positive, and minus WL over W over L times x squared. Here again, if we divide the W over L, because we are considering at point X, so we divide W divided by L, so that we get the load per unit length. Then times X, okay, times X, we get the WL times X becomes the load up to point X, and then we want the moment, so we multiply by X, so that's what we get. I should make a correction here. There is a 2 underneath here in the denominator, because W divided by L gives the load per unit length, times X gives the load up to point X. Now when we want to take moment, we should multiply it by X over 2. So we have W over L times X gives the load up to point x, and then times x over 2 gives us the moment. So I omitted this 2 in the previous slides, but I have corrected it here. Also I have corrected it in the PowerPoint as well. And if we substitute for w, which we have just obtained this, we get m is equal to that. Okay, so that you can simplify that m is equal to mo times that, and from the middle up to there, e to b, also x is greater than equal to l, smaller or equal to 2l, therefore m is equal to mo plus w over 4, 2l minus x, mo here because we have taken x from here, so mo is positive here, and w over 4 is rb times 2l minus x, and that is the moment in here, I mean the moment for this part to that part, because we have taken it in 2 parts because we have this distributed load here, so we have taken it up to there and there, but our section is here, x. So we have here m equal to m0. Again we substitute for w from there, and therefore for this domain also x between L and 2L, we get this relationship and that relationship, so we know the moments all over the place. As x increases, we can get m. You know, the bending moment distribution shown is parabolic over here, from there to there is parabolic, is a curve, but from here to there, because there is no load applied here, only load applied over there, so we get a linear line, and you can see if you put x equal to 0 here, you get m equal to n minus 1. If you put x 3/4 of L in here, then you get m equal to n0, and if you put x equal to 2L, you get m equal to minus n